Now, moving on, the second article investigated was robust representation and recognition of facial emotions using extreme sparse learning. Now, this scheme aimed to classify the 6 core emotions using video signals. So these 6 emotions were joy, anger, fear, disgust, surprise, and sadness. Now, an aside here quickly, what is sparse representation? So sparse representation is using a collective, as it's called, dictionary, which contains what's known as atoms, and we sum and scale those linearly to recreate our original input. So as you can see in this diagram right here, we have our dictionary, which contains these atoms. And in this case, the atoms are small little pixels, small little collections of pixels. And we sum those by what's known as the sparse coefficient, scale them and sum them by using what's known as the sparse coefficient vector to then recreate our input signal. Now, this scheme also used a fascinating technique called optical flow, which effectively mathematically models the motion of a person's head when they're expressing a given emotion. So for instance, if I'm moving my head like this while smiling, optical flow can mathematically model the motion of my head, and then analysis can be conducted to sense my given emotion. So 4 features were extracted in conjunction with the optimal flow. These are div, curl, projection, and rotation. Now, div measures the amount of local expansion or contraction of the facial muscles relative to the direction of the optical flow. So as I said, if my head is moving like this and I'm smiling at that time, div will measure the expansion and contraction of my facial muscles while I'm moving my head. Curl measures the dynamic nature of the local circular motion of the facial components. So for instance, we'll have a high curl associated with the corners of my mouth because when you smile, the corners of your mouth shoot up. Projection measures the amount of expansion or contraction of each point with respect to the nose. So in junction with curl, we would notice that, okay, based off my nose, if we move down from my nose and to the left and right, we're noticing a high amount of expansion or contraction, which means to the classification scheme that my mouth is moving. Then lastly, rotation measures the amount of clockwise or anti-clockwise rotation of each facial point with respect to the position vector. This once again works with the curl, but is focused more on the directional aspect of it. So am I smiling, where the tips of my mouth are moving respectively clockwise or counterclockwise, or am I frowning, where the tips of my mouth are moving anti-clockwise for their respective points? Now, using these 4 features, along with weighted and unweighted histograms of each, we achieve a pretty decent accuracy. With the weighted and unweighted histograms and all 4 features, we achieve a recognition rate of 95.33%, which is absolutely fantastic in terms of classification results. However, just using a standard descriptor, using the standard descriptor without the unweighted and weighted histograms, we can still achieve a recognition rate of 94.48%. However, it's important to note here that we are dealing with long processing times based off this at around 13.12 seconds. Now, the last scheme that we investigated is the spatiotemporal recurrent neural network for emotion recognition. Now, to start off, what we have to say is a recurrent neural network effectively takes its previous output as input to gather long-range contextual cues. Now, the recurrent neural networks in this scheme use both temporal and spatial information to output a result. So temporal information is effectively voice or any sound kind of waves or any change throughout time, whereas spatial information is what you can actually see and visualize. So whether someone is smiling, whether someone's frowning, but temporal would be, more indicative of the long range. So if you're in an argument with someone and things are progressively getting more and more heated, temporal cues will measure that change over time. Now, this particular scheme as well uses facial video signals or EEG data to classify the 6 core emotions. Here's a little scheme here's a little architectural scheme that breaks down what we're doing here. So we have our input and we first pass that through our spatial recurrent neural network. Now, this first recurrent neural network is multidirectional. So it can go in any given way to gather spatial information from any given direction in your video, or in your video frame, I should say. And then you develop a spatial projection based off your given direction. And then those are individually passed to the temporal recurrent neural network layer, which then is bidirectional. So you look at your past stuff and you look at your future stuff throughout as you're going. You once again get your spatial projection, and then you have your final softmax layer, which gives you your outputted result. Now, this once again offers incredible accuracy, being the most accurate scheme discussed today. So using the proposed approach, which is nicknamed the STRNN, we achieve an accuracy of 95.4% with this dual modality fusion. Now, that's very important to note. To get this accuracy, we need to combine both our video signals and the EEG data. Remember that for once more. Now, once we're discussing which scheme is potentially the best, we need to take in a variety of HCI concepts into account. Now, the four that I've chosen are the more fundamental ones, being accuracy, invasiveness, time complexity, and adaptability. Now, accuracy simply put is how correct our result is. Invasiveness is how invasive is it to human users? Does it propose any, difficulties for users? Is it, an inconvenience to them? Those kinds of factors are taken into account with invasiveness. Time complexity is simply how fast does it run? It offers no benefit if they have long processing times or, it takes years to train or converge or anything like that. And then adaptability is how easily it's implemented and how easily it can be integrated into our everyday lives. So comparing the differences between the techniques using these four factors, we see that our first article had moderate accuracy, but a high level of invasiveness due to the electrodes having to be placed on a person's head. Because of this, the adaptability suffers as well. Once again, to use this scheme, you have to place 62 electrodes on a person's head at one given time. However, to have some benefits, it did boast some fast processing times. Article 2 offered incredibly high accuracy while being extremely invasive, which is fantastic. All we need is a camera pointed at our subject in order to use this scheme. It did suffer from, slightly longer processing times, but because of that video camera being all that's needed, our adaptability is quite high as well. And in our last article, once again, accuracy was high, but because of the EEG signals that we need in order to get that accuracy, our adaptability is compromised as well. However, this scheme did offer moderate time complexities as well. So advantages and disadvantages, just being comprehensive here. Article 1, fast processing and decent accuracy, however invasive and not very adaptable. Same with Article 2. Uses two types of input data, but while boasting high accuracy, but incredibly invasive, and one data type is not easily adaptable. Article 2 offers low invasiveness with high accuracy, but suffers the longest processing times out of all three of these schemes. So taking all this into account, we need to say that our emotion recognition schemes could have a high level of accuracy, because if it doesn't, there's no added benefit. It should not hinder the user. It must be as non-invasive as possible, and it must augment their interaction with the computer. So to do that, processing times must be decent. And lastly, if implemented on a large scale, how easily it is adaptable and integrated into our lives. With these facts in mind, the optimal technique investigated, in my opinion, as I'm sure you could probably guess, is Article 2, robust representation and recognition of facial emotions using extreme sparse learning. Although it suffers from slightly higher processing times, the non-invasive nature of this approach, coupled with its high accuracy, makes it the optimal emotion recognition scheme. So normally this would be where I open it up to everyone for questions, but since this is just a video, I'll have the comments on below. So feel free to ask away and I'll answer all your questions as best I can. Thank you. So here are references, and with that being said, I hope you have a great day. Take care.